Uh, Good day, ladies and gentlemen. First of all, I'd like to express um, my gratitudes to Committee of the Congress for such opportunity to present my little ideas. First of all, I want to say that this is only the proposed scheme of modification of the parasporins. And this is my home city, Almaty, Kazakhstan. These are our beautiful mountains. And I'm from Scientific Center for Anti-Infectious Drugs. So, okay, let's start. So, let's begin from what parasporins are. They were obtained from Bacillus thuringiensis bacteria strain, and this parasporal inclusion in nature usually looks like crystal inclusions that solubilize in milk gut of insects, and under the protease degradation we have single toxins that have action against several kind of insects. So here you can see that this inclusion have square structure usually, and they are very familiar from strain to strain and have very similar diameters. And the main area of my investigations is searching for new anti-cancer parasporins that are obtained from different kind of bacteria, Bacillus thuringiensis. For example, the main activity has israelensis, and basically this strain has activity against mosquitoes, and maybe in this field we should seek for other parasporal inclusions with anti-cancer activity. A lot of strains were obtained from nature, but also we have several strains that that were in the space in International Space Station under this influence of the space, and then we obtained some parasporal inclusions from them and test for anti-cancer activity. So this is the structure of single monomers of these parasporal inclusions, and as you can see, they are very similar to other toxins from other bacterial origin. The first toxin that I will describe the modification of this parasporin, it calls parasporin 2, and it has three main domains. The first one is recognition domain, then transmembrane domain, and the membrane of and the domain that responsible for pore forming. And you see the mechanism of action a little bit later. Here I can say that another side area of investigation of anti-cancer parasporins is determination of recognition domain, because specific anti-cancer action, the responsibility of specific anti-cancer action is here, because other toxins don't have such such action. And mostly this recognition domain has aromatic amino acids that we think that responsible for the recognition. This is the mechanism of action of these toxins. These toxins are spore-forming proteins, and they require, for example, glycophosphatidylenoxytol anchor, GPI anchor protein. And now we think that they make their action only in lipid rafts. Here you can see the proof of specific action against only cancer cells. As you see, it's Sakai Kitada article from 2006. And here you can see that the fluorescent labeled parasporins interacts only with cancer cells, and histochemistry of tissues. You can also see that interaction is only in the areas of tumorigenesis. As personal communication, Professor Kitada, he's my supervisor from Japan. He said that he found that the anti-tumor effect of parasporin 2 and concentration of this to mice implanted mouse cancer cells. After injection, tumor size was significantly decreased. Under the influence of described dose, quarter of mice don't survive. So the scheme of proposed for modification of anti-cancer parasporins is based on more high permeability of vessels for high molecular compounds in foci of tumorigenesis with high concentration of proteases. This condition permits to create the construction composed from active parasporins, coupled with a linker particle having diameter of 40-50 nanometer via peptide bridge. Selective delivery of these conjugates to the foci of tumor formation with further proteolytic activation should decrease therapeutic dose of the active substance and decrease concentration in normal healthy organs and tissues with common vascular permeability, and resulting in decreasing of general negative effect for the organism. So this modification is based on the higher permeability of foci of tumorigenesis. As you can see from this picture, vessels have higher permeability for high molecular compounds, and concentration of proteases in these areas is much more higher than in vessels. So that is why we propose this the further scheme of modification. So this is the scheme of modification that contains active parasporin, and it coupled with, for example, PEG, polyethylene glycol, through the peptide bridge. The bonding between peptide and parasporin could be provided through the cysteine mutation. We have already done this mutation. This mutation allows us use sulfhydryl group of cysteine to bind with carboxyl group through the thioester bonding. Then another one end of the peptide will be binding with hydroxyl group through the carbamate bonding, and all these constructions, this conjugate, will have the size of 40 or 50 nanometers. These 40-50 nanometers, this size is mostly is useful for specific delivery the compounds to the loci of tumorigenesis. Then, because loci of tumorigenesis has higher protease concentration, this higher protease concentration becomes after the degradation of stroma cells. It's a really known condition, and these proteases should make proteolytic cleavage of this peptide bridge, and active parasporin should have its specific action without permeability in normal organs and tissues with common vascular permeability. What I'd like to add to this presentation, that this scheme of modification is also, as we think, also possible to use for to modify already known anti-cancer agents or anti-inflammatory agents to decrease their cytotoxic toxic effect to organism, because the concentration of these agents should be decreased during the treatment by specific delivery to the areas of tumor or inflammation. So this is that's short presentation. That maybe you have any questions. Yes.
I'm sorry, I missed the first part of your talk.
Yeah.
What made you think that this would be an anti-cancer?
Because these anti-cancer agents, parasporal inclusions, it's already proved that they have anti-cancer activity, especially against Hepg2 cells, and also during the in vivo experiments, it's been found that the size of tumor in mice is decreasing under the influence of these parasporal inclusions and parasporins. This work is ongoing from 1999 to this time, and it's been found more than 50 parasporins with anti-cancer activity, selective anti-cancer activity, without any hematological activity, how to say that is correct meaning, and without any action to normal cells, as for example MDCK cell line. And but there is only one problem, that in the case of in vivo experiments, quarter of mice die with unknown reasons. By unknown reasons, because all the tissues and organs have normal morphology, and we don't really know why do they die.
I mean, with this drug, the mice were normally healthy? eye?
No, with tumors, yeah. And to decrease this cytotoxic toxic effect of these parasporins, here I propose to modify it with this scheme of modification. Yes.
So if you make mutation, the point mutation on the top
Yes.
did you check the anti-cancer activity?
Yes, yes, we tried it, and it shows the same anti-cancer activity against HEPG2 cells with the same concentration. Yes, yes. Here we have one problem that maybe will be known only during the experiment. That after cutting this part, this peptide bridge, will this short tail after cutting, will it have any influence on the action of these parasporal inclusions?
Any questions from audience? Okay. I congratulate Almas Okassov for his well presentations. Thank you.
Thank you.